Let's talk about the law of radioactive decay, also known as nuclear decay. One of our followers from the Philippines asked us to explain this problem. How long will it take for 10% of a 1,000 gram sample of uranium-235 to decay? In order to understand this lesson, we must have an intuitive understanding of what is radioactive decay, derive the formula for radioactive decay, and then apply the formula to solve our problem. So let's begin with the first item for today. What is radioactive decay? Here is a model of an atom. At the middle is the nucleus, and surrounding the nucleus are electrons. Inside the nucleus are protons and neutrons. Protons are positively charged, electrons are negatively charged particles, while neutrons are neutral particles. The force that hold together the protons and the neutrons inside the nucleus is called nuclear force. And when the nuclear force is strong enough to hold this nucleus together, then we have a stable atom. But when the number of protons and the number of neutrons in an element is large, as in the case of uranium-235, holding together this large amount of protons and neutrons is harder. When there are too many protons, we have an unstable atom. Also, when we have too many neutrons, the atom is also unstable. That is when radioactive decay happens. There are at least 3 types of radioactive decay. One is called as the alpha decay, where alpha particles containing 2 protons and 2 neutrons are separated from the parent nucleus and thereby resulting to a daughter nucleus that has 2 protons less than the parent nucleus. And since the kind of element we have is dependent on the number of protons in the nucleus, then the resulting child nucleus here is now a different element than the parent nucleus. This new child nucleus now is 2 steps lower in the periodic table than the parent nucleus. And the particle that was separated is called as the alpha particle. That is why we call this as the alpha decay. The child nucleus could be in a heightened, excited state. And this state can result to a decay to a lower energy state by emitting gamma ray photon. There are instances when there are too many neutrons in the atom. Let's say in this isotope, we have more neutrons than protons. In this case, the nucleus emits an electron and an antineutrino in a process that changes the neutron to a proton. This neutron is now converted into a proton and an electron. The atom now keeps the extra proton and loses the electron. The loss of this electron resulted to high energy beta particle. That's why we call this as the beta decay. In some instances, instead of having many neutrons, there are too many protons. When this happens, the nucleus emits a positron and a neutrino in a process that changes a proton to a neutron, also known as positron emission. We call this decay as the beta plus decay. We also have other types of decay. For example, we have a cosmogenic process where sunlight turns nitrogen-14 into carbon-14, and we discussed that lesson in our video on radiocarbon dating. You have at least an idea of what is happening during the decay. The nucleus is decaying by giving away particles and thereby resulting in a lesser amount of mass. We call that as decay. The law of radioactive decay says that radioactive decay occurs as statistical exponential rate process. Quantum mechanics says that we cannot exactly determine when decay will happen, but if we have enough amount of identical atoms, then we can compute the decay by this law of radioactive decay. The law states that the number of atoms likely to decay in a given infinitesimal time interval, dn over dt, is proportional to the number of atoms present, where n represents the number of atoms. The proportionality constant, lambda, is called as the decay constant. We now write this statement this way. The number of atoms likely to decay in a given infinitesimal time interval, written as dn over dt, meaning the derivative of n with respect to t, is proportional to the number of atoms present. So the number of atoms present times certain constant. And we let that constant to be lambda. But since our rate of change represents decay, then our sign here must be negative. So we now have this first order differential equation. dn over dt equals negative lambda times n. Let's analyze this differential equation. There is a technique we call as separation of variables, where we pretend that dn is the numerator and dt is the denominator, and we can gather all the n variables at the left and the other variables at the right. We multiply both sides by dt over n. So what is left now at the left is dn over n, and at the right, we have negative lambda times dt. Then let's have some more space to solve this. In order to eliminate dn, we can take the antiderivative of both sides. Get the antiderivative of the right side. Negative lambda is a constant that we can pull outside the integral symbol, get the indefinite integral at the left side. The antiderivative of dn over n is ln of n plus a certain constant. Let's call the constant to be c. At the right side, negative lambda is a constant that we can pull outside the integral symbol, and the antiderivative of dt is t, so we have negative lambda times t plus a certain constant. Now, subtracting c sub 1 from both sides, c sub 2 minus c sub 1 will result to another constant also, and let's call that constant to be c sub 3. So this equation now can be simplified as ln of n equals negative lambda t c sub 3. Let's go to the next page. Let's take the exponential of both sides. We raise e to ln of n at the left side, and we raise e to this exponent, negative lambda t plus c sub 3. And so we now have this result. E and ln are inverse operations, so the left side results to n. And applying the law of exponent, this right side can now be written as e raised to this exponent times e raised to this exponent. But what is the value of e raised to c sub 3? C sub 3 is a constant. E raised to c sub 3 is just another constant, and let's call that constant to be capital letter C. This equation now looks like c times e raised to negative lambda t. Now in this equation t, let's find the value of this capital letter C. When time equals 0, the number of atoms is the initial amount of atoms present, and let's call that initial amount to be n sub 0. Substituting now these values to our equation, n of 0 equals the constant times e raised to negative lambda times 0. 0 times any number is 0, negative lambda times 0 is still 0, and e raised to 0 is just equal to 1. The right side would just be c, and the left side, n sub 0, is the number of atoms initially. So we now know what is the value of c. We can now replace this c by n sub 0 to arrive at this equation. The number of atoms present after t time is equal to the initial amount of atoms present at the start times the natural number e raised to negative lambda times t, where lambda is the decay constant. Our only problem now is to know what is the value of lambda. The value that is given is usually in terms of half-life. So we need to relate this lambda to half-life. So let's do that. From this equation that we just derived, let's divide both sides by n sub 0. So if you divide this by n sub 0, that will cancel out. And at the left, you have n of t over n sub 0. Then, at half-life, that means the ratio of the amount present now over the initial amount should be 1/2. So we can now replace this part by 1/2. We copy the right side. Now let's go to the next page. Let's get the natural logarithms of both sides. So we get ln of 1/2 equals ln of this right side. We are doing that because ln and e are inverse of each other and therefore results to 1. This right side would just become the exponent, and we copy the left side. ln of 1/2 equals this exponent because ln of e is 1. Dividing both sides by t over 2, we arrive at ln 1/2 over t over 2. So this formula now says that the value of negative lambda, which is the negative of the rate of decay, is equal to ln 1/2, which is a constant that we can find using our calculator, over whatever is the half-life of any given element. So if you know the half-life of, let's say, uranium-235, then we'll be able to determine the constant of decay lambda. Let's now summarize the formula that we have just derived so far. The first formula is our formula to determine the amount of atoms present after T time, knowing what is the initial amount of atoms present. This lower formula enables us to find what is the value of lambda, knowing the half-life of an element. These are the two formulas that we need in order to solve our problem for today. So let's go now to the problem. How long will it take for 10% of a 1,000 gram sample of uranium-235 to decay? This 1,000 grams is our N sub 0. This is the initial amount. And our N sub T would be whatever is the amount of atoms after subtracting this 10%. So let us now write our answer. So first, we identify that N sub 0 is 1,000 grams. The half-life of uranium, based on prior researchers' value, is given to be 703,800,000 years. This is the reason why it takes so long for uranium-235 to decay. The half-life of uranium-238 is more than 4 billion years. We are talking about uranium-235, which is usually used for nuclear reaction. Because this has a characteristic of being fissile, the atom can be divided by being hit by a fast-moving neutron. We also know that N sub T is equal to 900. We want 10% of this 100 gram to decay. So if 10% of the sample decayed, then the remaining value would be 90% of 1,000 grams, which is 900 grams. And we would like to know what is the time when from 1,000 grams, we will arrive at only 900 grams. At this time, already 10% of the 1,000 grams already decayed, resulting to only 900 grams left. The formula for negative lambda that we already derived previously is ln of 1/2 or ln 0.5 divided by the half-life. Here we know the half-life to be this value. And we also derived that the formula for radioactive decay is N of T equals N sub 0 times E raised to negative lambda T. So we know the value of N of T, we know the value of N sub 0, we can compute for the value of lambda, then the only thing for us to solve is T, which is what we want to find in this problem. So let's now do the necessary substitution. Our N sub T is 900, our N sub 0 is 1,000. Since we know that negative lambda is equal to this expression, we copy that expression and then copy T. Then substitute now this value to T over 2. So instead of T over 2, we now have this half-life of uranium-235, then copy all the rest. And then we simplify the equation by dividing by 1,000. This cancels out to be 1. 900 over 1,000 is 0.9, so we have 0.9 equals, copy this remaining part. You have here e raised to certain exponent. And we can eliminate this e by getting the natural logarithms of both sides. So get ln of the left side, ln of the right side. And again, by applying the power rule of logarithms, we can append this entire exponent in front of ln of e, and ln of e is equal to 1. So basically what is left at the right side is just this exponent. And so we copy the left side. And then solving now for t, we can multiply by the reciprocal of the coefficient of t. So we multiply this by 703,800,000 over ln of 0.5. And then we multiply the right side by the same number, 703,800,000 divided by ln of 0.5. ln 0.5 and ln 0.5 is cancelled out. Then this number divided by the same number equals 1. So what is left at the right side is t equals this ratio times ln of 0.9. And using now our calculator, we find that the value of this is equal to be 106,979,777 years. So this is the length of time for 10% of a 1,000 gram sample of uranium-235 to decay. Imagine 106 million years just to decrease 100 grams. So it takes that long to decay uranium-235. And it takes even longer to decay uranium-238, which has a half-life of about 4.5 billion years. That is why it takes that long to enrich uranium-238 to become a fuel-grade uranium-235. Time is very, very crucial to develop nuclear weapons.